In this short video, I'm introducing a new concept called work. And work is not the thing you do when you go mow somebody's lawn in the afternoon or help them move or go to the gym and lift weights. Well, it is going to the gym and lifting weights because we do physical work. But work is in the sense of physics work, and it is defined as force in the direction of motion, parallel, times the distance. So if I have a box sliding on a no friction surface and I move the box by applying an upward force like pulling a sled across some surface without friction, and I move it a distance d, in physics, how much work have I done? Well, work again is the parallel force, which in this case is the blue vector, and so using trigonometry, the angle between the horizontal, the x direction, is going to be the force F times the cosine of theta. So ka toa, adjacent side. So the adjacent side, the force I seek, divided by F is equal to the cosine of theta. So therefore, F cosine theta is the parallel force multiplied by distance gives me the work that I do. There are really two kinds of work that we want to consider right now, and work is strongly related to energy, as we're going to find out. What is the potential energy? This comes about when we lift an object against gravity. So to lift a box up, we have to overcome the weight. And again, you have to take it from the context that W equaling force times distance is not weight. It in this case is work. If you get confused, write the ORK for work. So I have a weight of mg and I have to lift against that. And so the work I do is the force in the direction of motion, which is upward in the y direction, is mg force times distance, which is height. So this is the work that I do in the vertical direction against gravity. So this does work when I lift an object against gravity. This does not do work, although it requires muscular energy to support the mass against gravity. I have to hold it here, my arm will get tired. But in the physics sense, I am not doing work because I'm moving. There is no force that is in this direction. The force is gravity perpendicular to it. So there's no work if I move the eraser side to side. There's work if I lift it up. How much work? It's weight, mg, times the distance. And if I drop the weight, I could tie it to a string and let it pull an object or wind a clock. You've seen pendula inside of grandfather clocks. As the pendulum falls, it moves the gears. It's doing work. We pull the weights up and we store in that energy, which is the work we do, is the stored energy against the force of gravity. And so as the weight falls, it will move the gears of the clock, which in turn move the hands to keep track of the time. So that is potential energy. When an object is here, it has potential energy to fall to the floor. If the object is here, it has potential energy to fall to this deck on the whiteboard. So there's another kind of energy. How much energy would it take to get this mass moving at constant velocity? And we'll say from rest. So from rest means that on our big four, we have D equals V0 plus V over 2 times time. But this is 0, so it's just Vt over 2. That's the distance from the big four. So I start with Newton's second law. How much work will it need? How much force times distance required to get an object moving at a certain velocity v? Well, Newton's second law says F equals ma, so that's mass times a, which is v over t, because v is delta v from rest. V minus 0 is delta v. So delta v equals v minus 0, which is just v, and divided by time. to get the definition of acceleration in change in velocity over time. And if I have to multiply by distance, mv over t times distance, the distance is just vt over 2. And so a little bit of cancellation, namely that the times cancel. So the energy is not related to the time it takes me, just the mass and the velocity, 1/2 mvv, 1/2 mv squared. And that is called kinetic or moving energy. So an object that's moving at a certain velocity, if I were to tie a string to it and allow the motion to stop, I could again allow this to do work. As I stop it to 0, it could pull something on a pulley, or it could wind a cord around a pulley. It could do some kind of work. But this is the energy that it has because it's moving. This is the energy that it has because the object has height. So there's potential energy, mgh, and kinetic energy, 1/2 mv squared. And these are to be memorized. They're not something you want to be deriving. You don't want to derive any equations on the test. You want to just use the equations. So work is the parallel force times distance, not this force, but the force in the direction of motion times distance is work. And work is related to energy, both in terms of the lifting work against gravity and the work to get an object moving at a certain velocity, v.